This is part two of a two-part video that addresses how to make use of variable assignments in predicate logic semantics. The first part dealt with how we can make use of the variable assignment to assign truth values to open well-formed formulas. This part will take a look at how we can make use of variable assignments and some other things to redefine the valuation function to handle quantified well-formed formulas. If you haven't taken a look at the first video, I'll put a link in the description below, so check that one out before you kind of continue here. So one thing we have is a solution to the first problem, which is we have a way of assigning truth values to open well-formed formulas using the notion of a variable assignment as well as the notion of a denotation. But we have a second issue, and that is that the truth values of quantified formulas are still unpacked in terms of formulas that make use of names. Let me give you a quick illustration of this. So the basic idea is that, let's say we have AX, CX. And let's just say, even though this is not an accurate translation, that this stands for everything or everyone is a curious cat. One way that predicate logic semantics is sometimes articulated is that this sentence, everything is a cat, is true if and only if every named cat is true. So CA, CB, CD, and so forth and so on. Every item that we can name is a curious cat. The issue here isn't that we don't have enough name, because the language of predicate logic provides you an infinite number. The issue is that there is no guarantee, or there's just this kind of unwarranted assumption that every item in the domain is named. Because obviously, if we say that everything is a curious cat, we can't simply mean only the named objects are curious cats, because you can imagine that there's a sort of stray cat, which is unnamed, that is not a curious cat, which would make this technically false, but our valuation function would make it true. So it would give us the wrong result. So there has to be this assumption that every item in the domain is named in order to really capture the requisite generality of this kind of claim. But that is really limits us to a specific language that has this specific feature that there isn't a kind of guarantee for in all cases. So what we would like, or what would be nice, is if we could unpack the truth value of quantified formulas without sort of taking these quantified formulas and specifying its truth or falsity in terms of other formulas that involve names. And so that's what the goal of this video is. So based upon what we've established before in a prior video, one initial kind of thought behind maybe how we might do this is to say that a quantified formula, and let's just take an existentially quantified formula, is true if and only if PA or for some name is true. So PX is true if and only if something like PA is true for some name. And so it doesn't have to be A, but some object that we can name, and since all objects are named, for someone it could be true. Or we could say that PX is true. So it could be one or the other. This existentially quantified expression is true, provided PA for some name is true, or PX is true. This is maybe a kind of thoughtful or promising approach because, as we've shown before, we already have a way of determining whether or not PA is true. We simply look to see if the interpretation of A is in the interpretation of P. And so that's simple enough. And in the last video, we talked about how we would determine the truth value of PX relative to this G variable assignment. And there we said that PX is true if and only if the denotation of X is in the interpretation of P. That is, if the object that the variable assignment assigns X to is in this extension of P. So if the object that X picks out is in P, then EXPX would be true. Another reason this is a kind of an attractive option is because it really makes the truth value of EXPX determined in a compositional way. That is, the truth value of the whole formula is determined by how we understand the parts. That is the truth value, not the truth value, but how we understand the existential quantifier and PX. Because you'll recall, rather than if we use names, we make the truth value of this universally quantified expression not determined by the truth value of CX, but determined by some operation we would perform on CX. That is replacing CX with, or replacing X with every single name and checking to see if for every single name that formula would come out as true. So this at least looks like a nice approach because we have a way of determining PX's truth, and it looks like it's determined in a more compositional way. But there is a problem with this. So the main problem is it doesn't give us the right result. And the way to see this is remember that the variable assignment G, it takes each variable and assigns each variable a single item from the domain. So it would take a variable like X and say, well, X refers to this specific object. The problem with this is that we don't think the truth of existentially quantified formulas like EXPX, they don't depend upon whether or not some specific object has the property P, but instead it has a sort of more indeterminate meaning, which is its truth depends upon whether there is at least one item that is P. So let me give you an illustration of this. So suppose we say that something is a cat. And intuitively, let's say this cat right here is in the domain of the objects that we're talking about, and it is also in the interpretation of cats. So we have this cat here, and we'll say that this is a stray cat. It doesn't have a name. So we have this domain, and it consists of a person, John, and this cat, Snickers, right here. Although I'm just calling it Snickers right now, but we'll just say that Snickers does not have a name. So John's a person, so he's not in the domain, and Snickers is a cat. Recall that we said that we can determine the truth value of EXCX by determining the truth value of simply CX. And we can do this using the variable assignment. But let's suppose that the variable assignment of X picks out John. And if it picks out John, then we know that X is not found in the extension or the interpretation of C. And if that's the case, then CX, that is X is a cat, is false. And if X is a cat is false, then something is a cat is false. But this gets us the wrong result because remember, we see that Snickers right here, this object, this stray cat that is unnamed, is in the interpretation of cats. And so EXCX, something is a cat, is true. So this initial approach gets us the wrong result, and so we'll need to make some sort of revision in order to fix this issue. So just to summarize, we can't specify the truth value of quantified formulas using single variable assignments. But if we had a way of, say, considering other variable assignments, then we could determine the truth value of these quantified formulas. And the way we would do that is if we considered not merely the variable assignment G. So we're not considering how a particular variable assignment G takes a variable and assigns it an object. But instead, if we had a way of thinking about G and considering every way of assigning X to items in the domain, that is, taking the general approach of variable assignments and changing them in some sort of way such that we can see not only how G, that is this particular variable assignment, assigns variables to object, but instead considering the variations of this variable assignment, considering multiple variable assignments relative to this initial variable assignment. So let's take a look at this in a little bit more specific. So the way forward is to introduce this variant variable assignment. And so let alpha here be a variable, and U is just some item in the domain of discourse. for a model. And so we'll define what we'll call a variant variable assignment. And we'll indicate it's a variant variable assignment by writing G, the variable at the top, and then the item from the domain at the bottom. And we'll say that this is this variant variable assignment is a variable assignment, just like G for the same model, except, so here's the way it differs. Here's the way we can kind of consider the variations of this variable assignment, except that this variant variable assignment, it assigns the item from the domain U to the variable alpha. That is, it takes alpha and says, I'm going to specify its reference or its denotation, and unlike, or at least let's specify that it's like G in every way, except for it'll take this variable and assign U to it. Let's look at some examples. So just to kind of get clear on how we should read these, here we have G, alpha is subscripted and U, or alpha is superscripted and U is subscripted. And we could read this as the variable assignment G, so it's just like G, except that the variable alpha is assigned the item U from the domain. Here, a little bit slightly more concrete, we have G super A, or super alpha sub 5, and this can be read as the variable assignment G, and it's like G in every way except for it takes the variable alpha. And unlike in this first variant variable assignment, which says alpha is going to denote U, this variant variable assignment assigns alpha the number 5, which is just found in some random domain. Let's look at a more specific example. So suppose we have a variable assignment, and let's call it G. Now I specified G up here, but I also provide it down here, so it's helpful to look at. So this G, this variable assignment, runs through all the variables. Here we're only going to deal with 3, and assigns it an item from the domain. So G, when it takes X as a input, it assigns U as a value. When it takes the variable Y, it assigns U2, and when it takes GZ, it assigns U3. Now let's consider the variant variable assignment. And this is like G in every way, except for it's going to assign the variable Y, the item U sub 1. So when the variable assignment G is a variant variable assignment that takes Y and assigns it the item U1, and then it takes the input X, it's going to behave identically to the original variable assignment. So you'll note that these two variable assignments, they assign X the same item. Let's move over to Z right here. So you'll notice that GZ assigns Z a item of U3, and this variant variable assignment also assigns Z a item of U3. The only difference comes about in how this variant variable assignment, what it does with Y here. And in this case, it assigns, instead of assigning Y the item U2, it says that Y denotes U1. So there's no difference between G and GY sub U1, except for how it's treating this Y variable. And in this case, it's taking Y, and instead of assigning U2, it's saying that Y denotes U1. One thing to note about variant variable assignments is that they might be identical to variable assignments. So suppose there's a variable assignment G, and just to run through this one really quickly, we have G again, it takes X, assigns it U1, GY assigns U2, GZ assigns U3. And now we have this variant variable assignment that's going to take X and assign it U1. So it's going to behave identical to G, except for it takes X and X will denote U1. So it's going to behave the same here and here. But when we look at the variant variable assignment, its treatment of X, we'll note that it behaves identically to the original variable assignment, because the original variable assignment took X and says that X denotes U1. Here we have the variant variable assignment. It takes x and says, in this case, we'll let x assign u1. And so when we're given x, it will assign x u1. So in this case, g is identical to gx sub 1. Even though here we have a variant variable assignment, it behaves identically to the original variable assignment. So that was a lot of terminology. What I want to talk about now, or at least ask now, is how can we use variant variable assignments to develop a new valuation function or modify our valuation function so that we can assign truth values to quantified well-formed formulas. So the plan is just to kind of present how we would define it for simple quantified formulas, look at the valuation rule in general, and then we'll come back and look at some examples. So let's say we have EXPX and we want to specify the condition under which it's true relative to the model and a variable assignment. So we'll say this formula is true provided there's at least one item U in the domain that would make PX true relative to this variant variable assignment that is relevant relative to a variant variable assignment that takes x. So it's going to take x and say that x denotes u. So provided there's at least one u that is in the interpretation of P, and if this were the case, then Px would be true. If Px is true given this, then the existentially quantified formula is true. Perhaps a simpler way of putting it is we are looking for a way that looking for a variable assignment where x denotes some item in the domain, and that item in the domain, if that item in the domain is in the interpretation of the predicate, then Px will be true. And if Px is true, then EXPX is true. If there is no item in the domain that we can let x denote that's found in the interpretation, then Px will be false, in which case EXPX is false. The procedure is the same for universally quantified formulas, but instead of looking for at least one item in the domain that we can let x denote, what we're doing instead is looking at every item in the domain that x might denote. And if for every item u in the domain that x can denote, Px comes out as true, then the universally quantified formula AXPX is true. Again, we'll look at some specific examples of this that are more concrete examples, but I wanted to kind of put the sort of formulation out there before looking at these examples. So next, let's just look at all of the rules together in terms of the valuation function. So here we have our valuation function as it's redefined. So we have an RL valuation for a model and a variable assignment. So we're relativizing a valuation function relative to these two items. And this valuation function is a function, and it assigns to each well-formed formula and predicate logic a truth value, T or F, not both, not neither, using all of these rules down here. And the ones I want to take a look at in particular are 1, 6, and 7. So the first rule is one we covered in the first video, which says that if we have an atomic well-formed formula and P is an n-place predicate followed by n terms, then we can say that this formula is true relative to a model and a variable assignment if and only if the denotation, the ordered tuple consisting of the denotation of the terms, is in the predicate P, that is in the interpretation of the predicate P. And so the idea here was if we have a formula like Px, we check to see if the denotation of x is in the interpretation of P, and if it is, then the formula Px is true. Whereas if it were PA, we check to see if the denotation of A is again in the interpretation of P, and if it is, then PA is true. And if it's not, then they're false. The ones worth looking at here, as we're putting it in more general terms, are the universal and the existentially quantified formulas. And here we're just restating it in more general terms. We say the universally quantified formula is true if and only if for every item in the domain, phi is true, where we take the variable, here we're specifying as alpha, and provided alpha can refer to any object and phi will come out as true, then the universally quantified formula is true. In the case of the existentially quantified formula, we say that this is true, provided that there's at least one item u in the domain that we can let the variable alpha reference, and this formula phi would come out as true. So if phi can come out as true for one of these variant variable assignments, then the existentially quantified formula here will be true. Okay, this is a lot to take in. I think you learn a little bit more by looking at some examples. So let's walk through some examples. So let's take a model, and the model consists of a domain and an interpretation, and the domain will consist of 5 objects. 1, 2, 3, 4, 5, so just 5 numbers. We'll have an interpretation of a one-place predicate, n, we could just let it stand for the numbers, and this is 1, 2, 3, 4, 5. O, it will refer to 2 and 4. We'll have an interpretation of A, B, C, and that will refer to 1, 2, and 3 respectively. Then we have the variable assignment G, which takes X and references 1, Y and denotes 2. And then if we had any more variables, we can just say that they are all assigned a value of 3. So now let's try to determine the truth value of EXOX using this model. So the truth value of EXOX is true because you'll notice that there is at least one item in the domain such that OX is true. There's one item in the domain such that OX comes out as true. That is, we can let this variant variable assignment GXU take X and assign it an item that is found in the interpretation of O. So let's kind of see how that's the case. One thing to note before we look at that is we definitely note that if we simply take the variable assignment of G, since G takes X and assigns it a value of 1, because if you come up here, you see G takes X and assigns it a value of 1, this would make it the case that OX is false. Because you'll notice when we look at the extension of O, that is the interpretation of O, we don't find the item 1 in there. And so if we simply took the variable assignment for X and tried to determine the truth value of EXOX using just the variable assignment, we would get the wrong result. What you'll note though is that there is at least one variant variable assignment, GXU, where EXOX would come out as true. And so let's look at just one of them. Consider the variant variable assignment GX2. That is the variable assignment that takes X and assigns it, or has X denote 2. And you'll note that 2 is in this domain up here. On this variant variable assignment, OX is true. Why is it true? Well, you'll notice that the valuation of OX relative to this variant variable assignment where X is assigned 2, OX comes out as true. And the reason this is the case is because you'll notice that when we go back up into the interpretation of O, we see that in this interpretation of O, 2 is found. As we see 2 right there. And so if X denotes 2, and 2 is in the interpretation of O, then OX is true. And since OX is true, we can say that the EXOX is true. So what we're doing here is simply looking for at least one variant variable assignment. We're looking for at least one item U such that we can let X denote that item. And if it's the case, there's that at least one that's found in the extension of O, that is found in the interpretation of O, then EXOX will be true. Let's look at another example. So let's take the same model. There's no real differences here. The only thing we're going to change here is the formula that we consider. And let's look at AXNX. You'll notice that AXNX is true since for every item in the domain, it's the case that NX equals true. And you can kind of check this. You can let X denote 1, and if X denotes 1, then NX comes out as true. If X here, under this variant variable assignment, if X denotes 2, you'll note that 2 is in the interpretation of N, and so NX is true. And you can kind of go down the list. Let's let X denote 5. We see that 5 is in the interpretation of N, and so NX is true. And so this gives us a way of not unpacking the quantified formula in terms of names, such as like NA, NB, NC, and D. All of these would have to be true for all of the names that we have in order for the universally quantified formulas. Instead, we make use of this variant variable assignment and let X just kind of move through the domain and potentially refer to any object and see, given those variations, is it the case that NX is true for all of them? So let's recap a little bit. So the problem with unpacking the truth value of quantified formulas in terms of named formulas was that there was no guarantee that every item in the domain was named. We could have these unnamed objects, and if we're unpacking the truth value of quantified formulas to say things about everything, we get the truth conditions wrong because we are making the truth conditions depend upon only the named things. And our problem with unpacking the truth value of quantified formulas in terms of variable assignments is that using a single variable assignment alone wasn't sufficient, because these variable assignments only take a variable and refer to one specific thing. We aren't letting it be treat it like a pronoun where it can potentially refer to any item in the domain. And so what we needed was not a single variable assignment, but a number of different variable assignments. We needed these sort of variations on a variable assignment. And so to solve this issue, we introduced the notion of a variant variable assignment and defined our valuation function with reference to these variant variable assignments. But one thing we might want to kind of wrap up with was we consider this cat along the way, and we might want to go back and look at this example. So remember this example, we had something as a cat, and we said that we had this formula EX CX. And in our original determination of this, we intuitively say that this is true, but when we ran through the valuation function, we came up with a value of false. So let's see if introducing this variant variable assignment will solve this problem. Again, we supposed a domain of John, and we have Snickers right here. We'll just kind of run this over here just so it's clear that here is Snickers the cat. Here he is a cat, and he is in the interpretation of kittens. And we also have this variable assignment GX, where G is the variable assignment that takes X and assigns X an item or denotes John. In this case, what we'll note is that EX CX is true. And the reason, this is kind of messed up here, this should be over here, but the reason EX CX comes out as true using this variant variable assignment is that when we take the valuation of CX, we are looking for at least one variant variable assignment, at least one item in the domain that we can let X refer to and see if CX comes out as true. And so we can consider a variant variable assignment that takes X. It's just like G, except for instead of it referring to John, which it did originally, we'll have it refer to Snickers here. And since this is a variant variable interpretation, when we take X, it's going to refer to this cat. And if X is now denoting this cat, then the formula CX will come out as true. And if this formula is true, then the EXCX is true. And so now we get the right result. The variant variable assignment allows us to take the variable X and denote the cat Snickers. And so it'll, instead of saying that EXCX is false, here we have EXCX coming out as true. So I just want to give a general summary about the two videos. Just a kind of recap of everything that's going on, because it's easy to get lost in some of the terminology. Under one presentation of the valuation function for predicate semantics, we take closed well-formed formulas and assign them a truth value, and we leave the truth value of open formulas undefined. In addition, the truth value of quantified formulas are unpacked in terms of unquantified formulas that make use of names. And this involved two problems. The first is that it just leaves these open well-formed formulas undefined, and we may want to have these formulas assign truth values. So introducing the notion of a variable assignment allows, and relativizing the valuation function to these variable assignments, these ways of assigning variables to items in the domain, allows us to specify the truth value of formulas like IXX, that is open well-formed formulas. And it also gives us a really tight relationship between syntax and semantics, in that if a formula is a well-formed formula, then we have a way of assigning it a truth value. Whereas before, if a formula was a well-formed formula, well, it might not have a truth value, especially in the case if it's an open well-formed formula. The second problem was that the predicate language assumed that there was a name for every item. So if we had an infinite number of items in the domain, there's this assumption that every single one of them is named. We solve this issue or this problematic assumption by relativizing the valuation functions to not only variable assignments, but also employing the notion of a variant variable assignments by considering all the different ways that the variables might be assigned items. We could specify the valuation function that no longer made it contingent upon whether or not an object was named or not. And recall here, the problem is not whether we have enough names. And if we're comfortable with the assumption that every item in the domain is named, then there isn't a whole lot of motivation here for all this extra notation. But if we're uncomfortable with that, if we like our logical system not to make this kind of assumption, then we saw that variables can ensure that each item is referenced in some way. That is, we can use the notion of a variable assignment and a variant variable assignment to pick out every single object in the domain. Another nice thing about this is that it really treats the language in a more compositional way, where the truth of the whole is determined by the truth of the parts. And so if we have an existentially quantified expression, EXPX, it's determined by the meaning of the existential quantifier and PX, rather than some operation that we might perform on it or some other formula. So the last thing I want to kind of point to here is just point to some additional resources. If something was unclear here, here are some books that I found helpful in formulating these slides and some of the handouts that this video depended upon. In addition, I'll put a link in the description to the slides themselves, or maybe an updated version of the slides, and as well as all of these books right here that I made use of. The first one is this book by LTF Gamut, which is a composition of authors, and they have a really nice explanation of the initial way of trying to assign truth values to formulas with free variables. And their presentation is really similar to how I presented it here, which is they give this sort of, here's how we might do it, and it runs into these two problems, and here's a kind of revision. So I encourage you to check this out, and I think our notation concerning this is pretty similar. Another book that is helpful, especially if you maybe don't have a problem with every item in the domain being named, is David Bostock's Intermediate Logic. This is a great book in general, so it's worth taking a look at. A third book that's was helpful for me is this book by Theodore Sider, Logic for Philosophy. I think this is a good book with respect to this particular issue, and so it's also worth checking out.